Swayam Prabha. Digital India. Educated India.
In our last lecture, we have seen a number of four-linked mechanisms, rather 4R mechanisms, the link dimensions of which were so fixed that a particular coupler point in each of these linkages could generate an approximate straight line, which we call approximate straight line mechanisms. That means the coupler curve had an approximate straight line portion, but it is known that by using four links we can never generate an exact straight line. In today's lecture, we will discuss what we call exact straight line mechanisms. So far as exact straight line mechanisms are concerned, we start our discussion with a mechanism which is known as Scott-Russell mechanism. The Scott-Russell mechanism is nothing but a slider crank or a 3R1P mechanism. This slider crank mechanism is of specific dimensions such that one point of the connecting rod generates an exact straight line perpendicular to the direction of the slider. We may think, what is the necessity of having a prismatic pair and then to try to generate a straight line? The thing is that the straight line will be generated perpendicular to the direction of the slider. This may be useful if I want to generate a straight line, but I do not have sufficient space to use a prismatic pair. Let us now discuss this Scott-Russell mechanism. This is, as I said, is nothing but a slider crank mechanism where the crank and the connecting rod are of same dimensions, and on the connecting rod on the extension of the connecting rod I take another point. Let us say this crankshaft is O2, crank pin is A, the slider is at B, and I take a point C on the extension of the connecting rod that is on the line AB, such that the lengths O2A, AB and AC are all same. We make crank length O2A is equal to the connecting rod length AB is also equal to the length AC. That is, the point C is chosen on the extension of the connecting rod such that AB is equal to AC, and we have started with a slider crank where the crank length O2A is same as AB. The direction of this prismatic pair is horizontal in this figure. What we can easily show that as this mechanism moves, this point C will generate a vertical straight line. It is obvious because AB is equal to AC is equal to AO2, these 3 points O2, B and C always lies on a circle whose center is at A and the radius is AO2, because AB is equal to AC is equal to AO2. That means these 3 points, namely B, O2 and C, will be always equidistant from the point A. So we can always draw a circle passing through these 3 points, namely C, O2 and B, whose center is at A. Now, as this is a semicircle, this angle will be always 90 degree. The angle between the line O2B and O2C is always 90 degree, because this is the angle on a semicircle. Therefore, if the line O2B remains horizontal, the line O2C will always remain vertical. That is, the point C will move along this exact vertical straight line. So this is what we call Scott-Russell mechanism. As we see, we are using a 3R1P mechanism, not a 4R linkage. Next, we shall discuss some exact straight line mechanisms using only R pairs. Obviously, we have to go for number of links more than 4, because 4R mechanisms can never generate an exact straight line. Exact straight line mechanisms using only R pairs are designed on the basis of a principle, geometric principle, which is called inversion. I would like to remind you that this principle of inversion should not be confused with kinematic inversions, which we have discussed earlier on many occasions. What is meant by this principle of inversion? What it says, that if 2 points say P and Q move on a plane such that the straight line PQ, that is the line joining these points P and Q, such that the line PQ always passes through a fixed point O and maintain a relationship, point O maintaining the distance OP into OQ a constant, then the curves generated by P and Q as they move are called inverse of each other. Let us see what is this principle of inversion. I am talking of 2 points P and Q which are moving in a plane. But the straight line PQ at all of these configurations passes through a fixed point O. Not only that, P and Q move in such a way that the distance of OP and OQ, the product of these two distances, remains a constant. In such a situation, the curve that is generated by Q and that generated by Q are called inverses of each other. It can be shown that if the curve generated by P is a circle, then the curve generated by Q will also be another circle. That means circles are inverses of each other. In general, if P generates a circle, say with center at OP as center. If P generates a circle with OP as center, then Q also generates another circle and vice versa. Say the center of this circle is OQ. It can be shown then these 3 points, fixed point O, the center of the circle generated by P, which is OP, and the center of the circle generated by Q, that is OQ, these 3 points also will be collinear. As we have just now said, let us say these are the 2 points P and Q, and these 2 points move in the plane of this paper in such a manner that this straight line PQ passes through this fixed point O. Not only that, this product of the distances OP into OQ remains a constant. As we see here, OP and Q. If P when comes here, when P comes to say P prime, Q will go to Q prime, such that P prime Q prime again is a straight line passing through O. Not only that, as OP has reduced, OQ has increased, such that the product OP into OQ remains a constant. In such a situation, if P generates a circle which I have called Kp, then Q will also generate another circle which I have called Kq. So these are the inverses of each other. Not only that, as we see in this figure, the center of the circle Kp is at OP, whereas the center of the circle Kq is at OQ. And these 3 points, namely the fixed point O, OP and OQ, are collinear. This is the inversion in general for circle. However, if the circle Kp passes through O, that is, the distance OOP is same as OPP. If the distance OOP becomes OPP, in such a situation, the circle Kp will pass through the point O. In that case, it will be very easy to show that this circle Kq becomes a straight line, that is, the radius of this circle becomes infinity. And this is what we will prove next, that if 2 points P and Q move in a plane such that the line PQ passes through a fixed point O and OP into OQ remains constant, and P generates a circle passing through the fixed point O, then Q will be generating a straight line, that is a circle of infinite radius. Let us now prove this special case of inversion, that is 2 points P and Q say passes through this fixed point O. This is the point P and this is the point Q, and we have OP into OQ is constant. we are talking of a special situation such that the point P, as it moves, generates a circle passing through O. As these 2 points P and Q move, the line PQ always passes through this fixed point, but P moves on a circle passing through O. In this situation, we will be able to prove that Q will move along a straight line. Which will be perpendicular to the diameter of this circle, which I named Kp, passing through the point O. To prove this, let us say this is O, the center of this circle of Kp, let me call it OP. The other end of the diameter of O, let me call it A. And if I drop a perpendicular from Q to this diameter OA, that is, this angle is 90 degree, let me call this foot of the perpendicular as T. Now, what we see that if we consider two triangles, namely OPA, which is a right angle triangle, and OQT, which is again a right angle triangle, these two triangles are similar. Why? Because the angle at P, this is 90 degree, angle at T is 90 degree. This angle is common to both the triangles OPA and OQT, which immediately implies that these two triangles are similar, because two of their angles are same, which will mean this angle is equal to this angle. Now, if these two triangles are similar, then we can write the ratio of their sides will be proportional. That means opposite to this angle, I have OP in this triangle. So, OP divided by opposite to this angle in the bigger triangle OQT, I have OT, should be equal to opposite to this right angle is OA and opposite to this right angle I have OQ. So, because these two triangles are similar, this relationship between the length of their sides will hold good. OP by OT is OA by OQ. From where I can write OT is OP into OQ divided by OA. We have already assumed that P and Q are moving in such a way that this distance remains constant, and OA is nothing but the diameter of the circle Kp, so that is also constant. So, this distance OT remains a constant. What is the implication of OT remains constant? As the point Q moves, that Q must be moving along this straight line such that the projection of OQ on OA remains constant. So, Q is generating this exact straight line, this So, this is a special case of that inversion when the circle generated by Q becomes a circle of infinite radius, that is a straight line. Now, linkages with only R pairs having more than 4 links have been designed to generate exact straight line using this principle, and those are called inversions. Because they use this principle of inversion, such exact straight line generators are called inverses. We shall discuss two such inverses shortly. Now we discuss an inverser which is known as Poiseuille's inverser or exact straight line mechanism. To follow this Poiseuille straight line mechanism, let me start with 4 equal links connected by revolute pairs, making a rhombus. Let me call this point P, this point A, this point Q, and this point B. This is a rhombus, that is all link lengths are equal, PA equal to AQ equal to BQ equal to PB. Now at A and B we connect 2 more links of equal length, call this point O. We attach 2 equal links OA equal to OB, and now make this point O fixed. So we have a figure with 1, 2, 3, 4, 5, 6, 7 links, and 1, 2, 3, 4, 5 revolute pairs, out of which A, B and O are revolute pair of higher orders, because at each of these 3 links are connected. At A, AP, AQ and AO, at B, BP, BQ and BO, and at O the fixed link O1 and the links OA and OB. So let me now try to figure out what is the, let me first make these link lengths equal, they don't look good. So let me now calculate the degree of freedom of this assembly. How many links we have? Link number n is 1, 2, 3, 4, 5, 6, 7. So n is 7. How many hinges we have? There are 2 simple hinges at P and Q, so J1 plus 2 J2. J1 is 2 plus 2 times. There are second order hinges at O because it is connecting 3 links, namely 1, 2 and 3, and 1 at B because it is connecting link number 3, 5 and 6, and 1 at O connecting link number 2, 7 and 4. So J2 is 2. So we have 3 into 2, 6 plus 2, 8. So the degree of freedom of this assembly is 3 times n minus 1 minus 2j, which is 3 into 6, 18, n minus 1 is 6, 3 into 6 is 18, minus 2 into j, 2 into 8 is 16, so degree of freedom is 2. So this assembly has degree of freedom 2. What is the implication of that? That I can take this point Q anywhere in this plane, because it has 2 degrees of freedom. I can give it any x coordinate and any y coordinate. That means this assembly can be deformed such that Q can be taken anywhere in this plane. Of course, restricted by the link length, but it can be independently moved in 2 perpendicular direction. That means Q can be taken anywhere in the neighborhood. Now, due to these geometric constants, that the figure APBQ is a rhombus and OA is equal to OB, what we find that however Q moves, these 3 points O, P and Q must lie on one line. Why? Because it is a rhombus, so the diagonals must intersect normally. This angle must always remain a 90 degree, because these are the 2 diagonals of this rhombus. PQ and AB are 2 diagonals of this rhombus APBQ. However Q moves, these diagonals will always intersect each other perpendicularly, so this angle will be 90 degree. Again, if I consider this APB, this is an isosceles triangle, because PB is equal to PA. So again, this line perpendicular must pass through P, because this is a isosceles triangle and this perpendicular to the base must be passing through the vertex. The same argument holds good for this isosceles triangle, namely OAB. So this perpendicular line to the base of this isosceles triangle AOB, this is at the midpoint. I am drawing a perpendicular. So this must pass through O, this must pass through P, which immediately implies that however this figure deforms, these 3 points, namely O, P and Q, must remain on one line. So we have satisfying that condition that P and Q, when they move, when P and Q move, O, P and Q remain collinear. That satisfies one of the conditions needed for inversion. Now we should be able to prove that OP into OQ also remains constant. To prove that, let me call this midpoint the intersection of PQ and AB. These 2 diagonals bisect each other perpendicularly at this point. Let me call this point D. So let me now try to calculate, however this figure moves, what happens to this product of these 2 distances OP into OQ. OP I can write OD minus PD, and OQ I can write OD plus DQ. Because the diagonals of a rhombus bisect each other perpendicularly, I can write PD is same as DQ. So this DQ, if I write as PD, I get OD squared minus PD squared, because DQ I can write OD plus PD, and OD minus PD into OD plus PD will give me OD squared minus PD squared. Now this I can write, I can subtract this AD squared from each of these terms. OD squared, because this is a right angle triangle, using Pythagoras hypothesis theorem, I can write OD squared is OA squared minus AD squared. So I can write this is OA squared minus AD squared. Similarly, PD squared, again this is a right angle triangle, so PD squared I can write AP squared minus AD squared. So this minus AP squared minus AD squared. AD squared cancels, so this gives me OA squared minus AP squared. So, this product, whenever this figure, however this figure deforms, OP into OQ remains OA squared minus AP squared. And now we note that OA squared, this is this longer link length, says L, and AP is this short link length, say S, which do not change as the figure deforms. So, however the points P and Q move, this remains a constant, which is the difference of these two link length squares, which is a constant. So, in this figure, what we have achieved so far by having this rhombus and these two sides equal is that O, P and Q always remain collinear as P and Q moves, where O is a fixed point. Not only that, however these 2 points P and Q move, not only they remain collinear passing through O, the product of the distances OP into OQ remains L squared minus S squared, which is again a constant, where L is this longer link length and S is this shorter link length. So, we have achieved two conditions required by this inversor. Only thing we have to ensure the locus of P is a circle passing through O. That will automatically ensure that Q will generate a straight line perpendicular to the diameter of that circle KP passing through O. It is very easy to ensure by adding one more link that P passes through a circle passing through O. To ensure that P passes through a circle passing through O, we draw a mid-normal to OP, perpendicular bisector to OP, and join a length, this point let me call OP, and join one more link which is OPP. As we see, because OOP is OPP, as the point P moves, it must passes through a circle, moves along a circle passing through the point O. And now we have completed what we call Poiseuille inversor. Now let us see how many links it has. We have added, we had 7 links to start with, and now I have added one more link, which is link number 8. So, N is 8, J, which is J1 plus 2 J2. What we have done, we have by having this link, we have converted this simple hinge, which we considered earlier, into a second order hinge, because now 3 links, namely 6, 7 and 8 are connected here. So, how many simple hinges are left? One at Q and one at OP. So, J1 is 2. And how many J2? 1, 2, 3, 4. So, J2 is 4. So, 2 into 4. So, J becomes 10, and degree of freedom of the entire assembly F is 3 times n minus 1, that is 7, minus 2 into J, that is 10, which is 21 minus 20 is 1. So, we have got an 8-link mechanism with single degree of freedom, where the dimensions are so chosen that Q will move along a straight line, which is perpendicular to this line OOP, because P is moving along a circle passing through O, and this is the diameter of that circle KP, which we called along the line OOP. So, when this mechanism moves, this 8-link mechanism moves, Q will move along a straight line perpendicular to this diameter of Kp. This is what we call Poiseuille inversor. Let me now recapitulate this Poiseuille straight line mechanism, What we did? We had this A, P, B, Q consisting of 4 equal link lengths. Say the link length is denoted by S. So we get a figure which is a rhombus. At A and B, we connected 2 equal links of say length L. OA is equal to OB is equal to the length L. We have seen that in this figure we can ensure that as this figure is deformed, P and Q move, but O, P and Q always remain along a straight line. Not only that, we have also seen when this figure is deformed, OP into OQ remains constant, OP into OQ remains constant and is equal to L squared minus S squared, where L is this longer link length, S is this shorter link length. In the next step, we added this link OPP to ensure that P moves along a straight circle passing through the point O, which I call KP. OPP is same as OPO. This ensures that P moves along a circle because this distance is constant and this is a fixed point, and because OPP is same as OOP, so that circle passes through the point O. In such a situation, this point Q will generate a straight line, that is, it will move along a straight line which is perpendicular to the line OOP. This angle is 90 degrees. This is what we call Poiseuille inversion. Suppose this OP is chosen elsewhere, somewhere here or somewhere there, then this condition still holds good, that PQ passes through a fixed point O, maintaining OP into OQ constant. Only thing that now P generates a circle, but that circle does not pass through O, and consequently the radius of this circle KQ is not infinity, it will be finite, and Q will move along a circle. We shall now demonstrate this Poiseuille inverser through a model. This is the model of that Poiseuille straight line mechanism which has 8 links, the fixed link and 4 links to make the rhombus, 2 links to make that isosceles triangle, and this is the extra link to ensure that this point passes through this fixed point O. This was our O, P, Q, A, B, and this is OPP. As we see, as this mechanism is moved, we will find that this point Q will generate this exact straight line. As this mechanism is moving, the point P is generating a circle which will pass through O. Consequently, this point Q is moving along this straight line. Now, if I remove this center OP from this particular point such that this distance is not the same as OPP, then P will move along a circle, but definitely will not pass through O. In that situation, if I remove this OOP and take it to some other location, then as we see, this point Q is going along this circular arc of very large radius, because all the conditions of inverses is being satisfied. OP into OQ is constant, OPQ always remain along a straight line, P is moving along a circle. Only thing, that circle is not passing through that fixed point because this distance is not equal to this distance. Consequently, Q will also move along a circle. In fact, we are able to get a mechanism such that I can draw circular arc of very large radius. In fact, this circle, the radius is very large. If I had moved this point to the other side, I could have generated this circle. But only when I make OOP is OPQ, the radius of the circle becomes infinity. This is of one curvature, this is the opposite curvature, and this is the no curvature. If I call it positive curvature, negative curvature, and zero curvature, which means a straight line, that is a circle of infinite radius. This is what we call a Poiseuille straight line mechanism. Only if I ensure that OOP is OPP. We have just now discussed Poiseuille straight line mechanism, which consists of 8 links and all are pairs. Now we discuss another inversor, which is known as Hart's inversor or Hart straight line mechanism. As we will see, this will have only 6 links instead of 8 links, as we have seen in case of Poiseuille mechanism. To explain the Hart's inversor, let me start with an antiparallelogram. Let me call this figure A, B, C and D. In this AD, this link length is equal to BC, the other link length. Let me call it S, and AB is equal to CD, which is a longer link length. Let me call L. So we start with a antiparallelogram, that means the opposite sides are of equal length, but it is in the crossed configuration. Now on this link AD, let me take a point O and make it fixed. This point let me call O. Now if I find the degrees of freedom of this assembly, what we see, we had 4 links and a fixed link. So n is total number of links, n is 5, and we have 1, 2, 3, 4, 5 simple hinges. So j equal to j1 is also 5. So the degree of freedom is 3 into n minus 1, that is 3 into 4, minus 2 into j, that is 2 into 5, which is 2. So again we find this figure is deformable. That means I can take these points B or C or D anywhere in this plane, restricted only by the link lengths. But however this figure is deformed, this BC will always be remaining equal to AD and AB will remain equal to CD. That means the parallelogram will remain always parallelogram, however this body deforms. Consequently, I can say that because it is antiparallelogram, BD will always remain parallel to AC. Now through O, I draw a line which is parallel to these two lines, namely BD or AC. Where this line intersects the line AB, let me call it P, and this point of intersection let me call Q. As we see, the point O is not moving, and however the figure deforms, this line will always remain parallel to BD and AC. That means these 3 points, namely O, P and Q, always remain on one line. So one condition of the inversor is being satisfied, that P and Q move, but PQ, the line, always passes through the point O. Not only that, we will be able to show that whenever this figure is deformed, OP into OQ remains constant. To prove that, let me proceed as follows. I draw a line through B parallel to AD. Let me call it E. So, AEBD, this figure will be parallelogram because BD is parallel to AE and I have drawn BE parallel to AD, which means AD will be also equal to BE because they are opposite sides of a parallelogram, and OE will be equal to BD. Now, BC is also equal to AD is also equal to BE, so I get a isosceles triangle BEC. So, I drop a mid normal from B onto EC and let me call this point F. Let me say BD, this distance is X, which keeps on changing as the mechanism moves, as this assembly moves, and AC, let me call it Y, which is also changes. BD, I write X, and AC, I write Y. So, in this figure, let us see that APO and ABD, these two triangles will be similar because this line OP will always remain parallel to BD. So, what we can write, OP by X is same as OA by AD. So, considering these two similar triangles, namely OAP and ABD, because this line is parallel to this line, I can easily write OP by X is OA by AD. Now, let me consider these two triangles, namely DOQ and DAC. Again, in these two triangles, OQ is parallel to AC, so these two triangles will be also similar. So, what I can write, DO, that is OD divided by DA, AD is same as OQ by Y. OQ by AC, which I called Y. Now, let me cross multiply these two equations, then we can see what we get is OP into OQ is XY into OA into OD divided by AD squared. If I multiply these two equations, I get OP into OQ is same as XY into OA by AD into OD by AD, which is OA into OD by AD squared. Now, in these expressions, as you see, when this figure is deformed, the link lengths OA, OD or AD never changes. So, this factor is a constant. So, if we can show that XY remains constant, that will imply OP into OQ also remains constant. So, to maintain the second condition of inversion, that as these points P and Q move, not only the line PQ passes through O, the distance OP into OQ remains constant, will hold good only if I can show that whenever this figure is deformed, this product XY, that is BD into AC, remains constant. Let me show that. That is quite simple. We have to show that XY remains constant. What is XY? XY is BD, which is same as AE. So, X is AE. And what is Y? Y is AC. So, XY is AE into AC. This I can write AE is AF minus EF and AC is AF plus CF, which is same as EF, because this is an isosceles triangle, this is the perpendicular bisector, so this is equal to this. So AF plus FC, that I can write AF plus EF. So this we get AF squared minus EF squared. Now AF squared I can write, because ABF is a right angle triangle, so AF squared I can write from Pythagoras theorem AB squared minus BF squared. Similarly, EF squared I can write minus EF squared, from this right angle triangle I can write BE squared minus BF squared. So BF squared cancels, we get AB squared minus BE squared. And BE is same as AD, because this figure is a parallelogram, so I can write AB squared minus AD squared. Now AB I called L and AD I called S, which are link lengths. So however the figure is deformed, they never change. So what we have done so far, we have first seen OP into OQ is XY into some constant in terms of the link lengths. So if XY remains constant, then OP into OQ will also remain constant. And however the points PQ move, the line PQ passes through O. This is constant, which implies OP into OQ is also constant. Consequently, we are satisfying all the conditions needed by inversor. Now, if we ensure that the point P moves along a circle passing through O, then Q will generate, this point Q on this link CD will generate a straight line. As in the case of Poiseuillean mechanism, now we add one more link so that the point P is guided along a circle passing through O, which is simple. We draw the mid-normal of OP and this point we call OP, and here we put another hinge and connect by a rigid link. Because OPP is OOP, so P will go along a circle which OOP as radius, OPP as radius, and that circle passes through O. So the third condition of straight line inversor is also satisfied. Consequently, if this mechanism moves, the point Q will generate a straight line which will be perpendicular to the line OOP. Q will generate a straight line which will be perpendicular to this line OOP. Let us see how many links we have got in the Hertz inversor. The fixed link, these 4 links that constitute the first antiparallelogram, and I have added one more link. So N is 6. Let me count J is J1 plus 2 J2. As we see, we have 1, 2, 3, 4, 5, 6 and 7, and all of them are simple hinges. There is no J2, J2 is 0 and J1 is 7. So J is 7. So the degree of freedom of this is 3 into 5 n minus 1 minus 2 into J is 1. So again we get a 6-link single degree of freedom mechanism consisting of only R pairs, and when this linkage moves, this particular point Q on this link CD will generate an exact straight line. This is called Hertz inversor. Here again, if I don't take OP in a manner such that OPP is OOP, then P will generate a circle, Q will also generate a circle. But as soon as I make this distance equal to this distance such that P moves along a circle passing through O, then Q circle radius of the circle of Q becomes infinity, which means Q will be moving along a straight line, because straight line is nothing but a circle of infinite radius. Now we will demonstrate this Hertz inverser through a model. This is the model of the Hertz inverser, which is a 6-link mechanism. As we see, the fixed link, link number 2, 3, 4, 5, and this is the 6th link. These two link lengths are same and these two link lengths are same, constituting an antiparallelogram. The opposite sides of this quadrilateral are same, but that is in a crossed configuration. This is what we call A, B, C, D. Now we take one point on this link fixed. Then think of a straight line which is parallel to this line and this line. Because this is an antiparallelogram, these two lines will always remain parallel. And I think of a line passing through this fixed point O, which is parallel to this line and this line. The intersection of that straight line drawn through O with this link I call P, and this is the intersection of that straight line with this link, which I call Q. Now I make OP is OPP. This link length, this point OP I choose on the perpendicular bisector of these 2 points, such that OPP is OPO. Consequently, P will go along a circle with this point as center and this as radius, and that circle will pass through this point O. As a result, since OP into OQ remains constant, which we have proved, PQ passes through this point O in all configurations that we have shown, so Q will generate a straight line. As we can see that this point Q will generate this straight line. As we see, this point Q is generating this straight line. So this is Hertz inverser, which is a 6-link chain as compared to a Poiseuille inverser, which was an 8-link mechanism. Let me now summarize today's lecture. We have discussed today only exact straight line mechanisms. We started with Scott-Russell mechanism, which is a simple slider crank mechanism, that is a 3R 1P linkage, where the length of the connecting rod and the length of the crank was equal. In such a situation, if we take a point on the extension of the connecting rod suitably, then we found that that point on the connecting rod generates an exact straight line perpendicular to the direction of sliding of the slider. After that, we discussed the principle of inversion, and I remind you again, I would like to emphasize it, that do not confuse this principle of inversion with kinematic inversion. We have explained this principle of inversion and used that principle to generate 2 exact straight line mechanisms using only R pairs. We discussed 2 of them, namely Poiseuille straight line mechanism, which has 8 links, and then Hertz straight line mechanism or Hertz inverser, which has only 6 links.